Welcome to this lecture on calculus, where we will be exploring Euler's theorem. Imagine you are baking a giant cake for a party. If you double the amount of flour, sugar, and butter, the final weight of the cake exactly doubles. This idea of perfect scaling is everywhere in mathematics and physics. Today, we will learn how Euler's theorem gives us a brilliant mathematical shortcut to understand these scaling systems without doing incredibly long, complicated calculus operations. Let us dive in. Before we can use Euler's theorem, we must formally define what a homogeneous function is. Why does this matter? Because Euler's theorem only works on systems that scale in perfect harmony. A function is called homogeneous if whenever you multiply all of its input variables by a constant scaling factor, the entire function gets multiplied by that factor raised to a specific power. Think of a flat square. If you double its dimensions, its area increases by a factor of 4, which is 2 squared. That makes the area a homogeneous function of degree 2. Now that we understand the concept of perfect scaling, let us look at its mathematical form. The formula states that f of t times x and t times y equals t to the power of n times the original function f of x and y. Here, t is our scaling factor, which is just a plain number we use to multiply our inputs. The letter n represents the degree of homogeneity. This degree tells you exactly how the output reacts to the scaling of the inputs. If n equals 1, the function scales linearly. If n equals 3, doubling the inputs would multiply the output by 8, since 2 to the third power is 8. To make this formula more concrete, let us visualize what it means for a function to be homogeneous. On the screen, you see a small square with side lengths x and y. Its area is simply x times y. When we scale the inputs by a factor of 2, we get a larger square with sides 2x and 2y. Notice that the new area is not just twice the original, it is 4 times the original area. The scaling factor of 2 is raised to the power of 2, which is the degree of homogeneity for this area function. This geometric idea perfectly matches our algebraic formula. With a solid grasp of homogeneous functions, we are ready for Euler's theorem itself. Why is this theorem so important? Leonhard Euler discovered that for any homogeneous function, there is a beautiful, exact balance between the function itself and its partial derivatives. Remember, a partial derivative is simply the rate at which the function changes when you tweak just one variable while keeping all others completely frozen. Euler's theorem gives us a direct shortcut. Instead of calculating a complex combination of derivatives manually, the theorem tells us that this combination is directly proportional to the original function. It is a massive time saver. Let us look at the exact mathematical statement of Euler's theorem. The formula says that x times the partial derivative of f with respect to x plus y times the partial derivative of f with respect to y equals n times the original function f of x and y. Here, x and y are our independent input variables. The partial derivative terms represent how fast the output changes when only one specific input changes. The letter n is the degree of homogeneity we found earlier. This formula is incredibly powerful because it tells us that we can find a complex combination of rates of change just by multiplying the original function by a single number n. Before we trust this formula, let us verify it with a straightforward example to build confidence. We are given the function f of x and y equals x cubed plus y cubed. Our first step is to prove the function is homogeneous and find its degree. We replace every x with t times x and every y with t times y. Expanding the cubes and factoring out t cubed reveals our original function. This proves the function is homogeneous with a degree of 3. Next, we manually calculate the partial derivatives. Treating y as a constant, the derivative with respect to x is 3x squared. Similarly, the derivative with respect to y is 3y squared. Continuing with our verification, we now take those partial derivatives and plug them into the left side of Euler's formula. We multiply x by 3x squared and add y multiplied by 3y squared. Simplifying this, we get 3x cubed plus 3y cubed. Finally, we factor out the common number 3 from both terms. The expression inside the parentheses is exactly our original function. So the result is 3 times f of x and y. Since our degree n was 3, this perfectly matches the right side of Euler's theorem, which is n times the function. We have successfully verified that the theorem works exactly as promised. Now, let us look at a problem where calculating the derivatives manually would be a nightmare. We are given a complex rational function u and asked to evaluate a specific combination of its partial derivatives. If we tried to solve this by brute force, we would have to use the quotient rule, creating a massive, ugly fraction. Instead, we recognize that the expression we need is exactly the left side of Euler's theorem. Our strategy is simply to check if the function is homogeneous. We substitute t times x and t times y, expand the powers, and factor out t to the fourth power from the numerator and t from the denominator. Continuing our shortcut, we simplify the scaling factors using the rules of exponents. Dividing t to the fourth by t leaves us with t cubed on the outside. The fraction inside the parentheses is our original function u. This proves the function is homogeneous and the degree n is 3. Because it is homogeneous, Euler's theorem guarantees that the complex derivative expression is simply equal to n times the original function. We can now write down the final answer immediately as 3 times the original fraction. We completely avoided the quotient rule and pages of messy calculus, turning a difficult problem into a simple algebra check. Now that we have used this formula, let us understand where it comes from. In calculus, we never just accept a formula. We must prove it. We will derive Euler's theorem starting from the fundamental definition of a homogeneous function. To see how the function changes as the scaling factor changes, we take the derivative of both sides with respect to t. During this step, we treat x and y as constants. On the right side, the function acts as a constant multiplier. So we just use the standard power rule on t to the power of n, bringing n down and reducing the power by 1. The left side is more complex and requires the chain rule. Continuing our derivation, we apply the chain rule to the left side. We differentiate the outer function with respect to its slots and multiply by the derivative of the inside terms with respect to t, which gives us multipliers of x and y. Now we have an equation that holds true for any value of the scaling factor t. Because we want a relationship for our original variables without any scaling factor cluttering the equation, we simply choose to set t equal to 1. This means we are looking at the function in its original, unscaled state. All the complex scaling factors completely vanish, and we arrive exactly at Euler's theorem. This elegant relationship is a direct, logical consequence of how homogeneous functions scale. So, we have proven that Euler's theorem holds for two variables. This brings us to an important generalization. The beauty of Euler's theorem is that it is not restricted to just two inputs. In the real world, systems often depend on many different factors. If a function has 3, 4, or even 100 variables, and it scales uniformly across all of them, Euler's theorem still applies perfectly. We just keep adding terms for each new variable. For every single variable, we take the partial derivative, multiply it by the variable itself, and add it to the running total. No matter how many variables you have, they will perfectly sum up to n times the original function. Beyond adding more variables, we can also go deeper into the derivatives themselves. Sometimes we need to look at second-order partial derivatives. A second-order derivative tells us how the rate of change itself is changing, much like how acceleration tells us how velocity is changing. Euler's theorem can be extended to connect these second-order derivatives. Why is this useful? Because calculating second-order partial derivatives manually for complex functions is notoriously long and highly prone to algebraic mistakes. The extended theorem gives us a direct shortcut to the final answer, bypassing the tedious calculus entirely. Let us examine the formula for the extended second-order theorem. The equation involves x squared times the second derivative with respect to x plus 2xy times the mixed partial derivative plus y squared times the second derivative with respect to y. Notice how the coefficients on the left side match the pattern of expanding a binomial squared. On the right side, the original function is now multiplied by n into n minus 1. This formula allows us to evaluate a massive, complicated sum of second derivatives instantly, just by knowing the degree of homogeneity n. It is an incredibly powerful tool for advanced calculus. Before we prove this new formula, let us see it in action. We will use the exact same rational function from our previous example. This time, we are asked to evaluate a massive second-order differential expression. This looks incredibly intimidating at first glance. Calculating these second derivatives manually would take hours and likely result in errors. However, we already know from our previous work that this specific function is homogeneous, and we already found that its degree n is 3. We can use this knowledge to completely bypass the calculus. Continuing with our shortcut, we simply plug our degree n equals 3 into the right side of our second-order formula, which is n times n minus 1. We evaluate the subtraction inside the parentheses first, giving us 2. Multiplying 3 by 2 gives us 6. This number is our final scaling multiplier. This means the entire massive combination of second derivatives is simply equal to 6 times the original function. We can write down the final answer immediately. With almost zero effort, we evaluated a highly complex expression. This transforms an impossible calculation into a trivial one. Now that we have seen how useful the second-order theorem is, let us understand where it comes from. To prove it, we start with the original first-order Euler's theorem that we already proved. We will differentiate that entire equation with respect to x to generate the second-order partial derivatives we are looking for. When we differentiate the left side, we must use the product rule on the first term because it is a product of x and a derivative that depends on x. For the second term, y is treated as a constant. The right side simply becomes n times the derivative of f with respect to x. Continuing our derivation, we want to isolate the terms with second derivatives. We move the single first derivative term to the right side and factor it out, grouping our first-order derivatives neatly. Next, to build the full second-order theorem, we multiply this entire equation by x. This makes the first term x squared, matching the pattern we want to prove. Now, by following the exact same logic, if we had differentiated the original theorem with respect to y instead and multiplied by y, we would get a perfectly symmetrical equation for the y variables. This symmetry is a hallmark of homogeneous functions. For the final step of our proof, we simply add these two symmetrical equations together. On the left side, the two mixed derivative terms combine to give us 2xy times the mixed derivative. On the right side, we factor out the common term n minus 1. Look closely at the expression inside the parentheses on the right side. That is exactly the left side of our original first-order Euler's theorem. We know that expression is equal to n times f, so we substitute n times f into the parentheses, and we arrive at our final second-order formula. The proof is complete. So, we have proven these theorems, but why do they matter outside of a math class? Euler's theorem is a fundamental principle used across many scientific disciplines. In economics, it is the mathematical backbone of marginal productivity theory. If a factory's output scales perfectly with labor and capital, Euler's theorem proves that paying each input its marginal contribution will perfectly exhaust the total output. In thermodynamics, properties like volume and internal energy scale with the size of the system. Euler's theorem allows physicists to relate the total energy of a gas directly to its temperature and pressure without tracking every single molecule. It makes modeling complex systems possible. To summarize our lecture, Euler's theorem provides a direct bridge between a homogeneous function and its partial derivatives. We learned that a homogeneous function is simply one that scales uniformly. When this condition is met, the sum of each variable multiplied by its respective partial derivative is always exactly equal to the degree n times the original function. This theorem, along with its second-order extension, serves as a powerful shortcut. It allows us to bypass tedious differentiation and instantly solve complex problems. You now have a master key for understanding any system that scales. Thank you for watching.